did this correctly. Okay. All right, so we are continuing our talk about gradient descent as an optimization method. And so kind of up until now, the way we've optimized our loss function was that we found the gradient, or we found the derivative, and we set that equal to 0, and we solved, for our value. And now, we're introducing gradient descent as kind of this iterative computational method for finding a local minimum. And it does not require us to solve for where the derivative is equal to 0. Okay, so so this is a slide from before, but the idea is that even if you can find the derivative, or even if you can find the gradient, it might be difficult to set that equal to 0 and solve. Okay, that equation of solving for where the gradient or derivative is equal to 0 might be difficult. And so we will use gradient descent as a way to iteratively get closer to the gradient. Okay, and so this is the basic algorithm. You have some location W. You find the gradient at that location W sub n. So you're at some location W sub n. You find the gradient at that location W sub n, and you take a step in the opposite direction. Okay, so the gradient points to the in the direction of greatest increase of the function, and so if you move in the opposite direction, you'll be moving in the direction of the greatest decrease of the function. Okay, at that point location, and so gamma is some kind of constant representing how big of a step you're going to take relative. And this is going to be something that you have to adjust depending on the function that you're working with. But this is it. Okay, this is the entire algorithm. Your next location, W sub n plus 1, is going to be your current location with a step moving in the opposite direction of uphill. Okay, and then so you take a step. Now you're at a new location. You figure out which way is uphill, and you take another step downhill. Okay, so this is, so I'm going to just kind of work through some examples to kind of illustrate how this works. So here I'm going to just start off with an arbitrary two-dimensional function. Okay, so this is a function of x1 and x2, and it looks like this: x1 squared minus 2x1 minus 0.5x1 x2 plus 2.5 x2 squared. And so if you want to find the gradient of f, it's basically going to be, the gradient of f with respect to x, okay, x being a two-dimensional vector, your gradient is also going to be a two-dimensional vector, okay? So x consists of x1 and x2. The gradient will consist of df dx1 and df dx2. So if we take this, the partial derivative with respect to x1, we get 2x1 minus 2 minus 0.5 x2. Okay, and if we take the derivative of this with respect to x2, we get minus 0.5 x1 plus, and then because it's x2 squared, we're going to get 5 x2. Okay, so this should be, so these are the partial derivatives with respect to x1 and x2, and thus we have our gradient, which is two-dimensional. All right, so here's just a contour plot of that function, x1 squared minus 2x1 minus 0.5 x1 x2, and so on and so forth. And this is kind of what it looks like in 3D. So it's because our largest terms are x squared terms, it basically just looks like kind of a bowl, okay? And so if we wanted to find the gradient, okay, we would just plug in -5 and 4, and I'm missing a negative sign here. I've got to fix that. Okay, so -0.5x1 plus 5x2. Okay, so here we are. And then so we just plug in -5 and 4. And so if we have 2x1 minus 2 minus 0.5x2, I plug in -5 here and I get -14 for the partial derivative of f with respect to x1. And then I get, when I plug in -5 and 4 over here, I get 22.5, okay? And that's the partial derivative of f with respect to x2. All right, and so if we do this, okay, so if we apply gradient descent, so here we're at x1, x2 at time 0, okay, and we want to know x1 and x2 at time 1, then what this looks like is we take x1 and x2 at time 0 minus the gradient of f at that time. So we're going to have -5, comma 4, which is our current location, and then here I'm going to use a gamma of 0.1. You can use different sized gammas, and we'll talk about what that looks like. So if I apply -0.1, here I'm going to get -14 and 22.5, and that becomes +1.4 and -2.25. And so our next location will be -5 plus 1.4, which is -3.6, and 4 minus 2.25, which gives me 1.75. So this is going to be my next location after I've updated my gradient. And so if I wanted to code this up, it's going to look like this. So I code in x1 squared minus 2x1 minus 0.5x1 x2 plus 2.5 x2 squared. Okay, so that's our function f. And then the gradient of f is 2x1 minus 2 minus 0.5 x2. And here I have minus 0.5 x1 plus 5 x2. Okay, and then so the gradient, so the f will return just a single value, and the gradient will return 2, because you've got the gradient with respect to x1 and the gradient with respect to x2. All right, so if I plug this in, let's say I start off at -5 and 4, then I can say gamma is 0.1. The gradient is going to be I plug in -5 and 4, and indeed I get -14 and 22.5, which is what we have here, -14 and 22.5. And then if I take our starting location and I subtract off the gradient times the gamma, which is 0.1, indeed we get what we found to be -3.6 and 1.75. So this is just a matter of just typing in, typing in exactly what we have here into a function. And then now I'm applying this. Is this okay? And so if I plot this, so I start off at -5, comma 4, which is up here, and then the next location there is going to go to -3.6 and 1.75. If you plot your contour lines, a property of the gradient is that assuming you have equal aspect ratio, the gradient is perpendicular to the contour line, okay? Because the contour line shows kind of the trace of the locations where the values do not change, and and the gradient is going to point in the direction of steepest ascent or steepest descent. And so the gradients are perpendicular to the contour line at this location, if there were one. If I think it's 85. If I plotted the contour line at 85, immediately right there would be a right angle. Okay, and so here it points down to here, and then we would start here for our next iteration at negative 3.6 and 1.75, and we would repeat. So then now my starting location would be negative 3.6 and 1.75. I would calculate the gradient there, and then I would just repeat the calculations. Maybe it's not that hard to do. I think bless you. So just calculations. Next iteration is negative 3.6, 1.75, okay? And and so the gradient at negative 3.6 and 1.75 is negative 10.075 and 10.55, and then the location after that will just be that, okay? Calculations at the next iteration. Okay. If we wanted to just do a few more iterations, so here I'm doing 20 iterations. I'm creating a matrix called locations, all right, which is going to have, because I'm doing 20 iterations, it's going to have 20 rows and 2 columns, 1 column for x1 and 1 column for x2. And I'm going to start at negative 5, 4. And in my loop, all I'm going to do is I'm going to just store my current start location, this x vector, and store that into the ith row, the first row of the matrix. And then I apply gradient descent, which is exactly this. You know, your current x location minus gamma times the gradient there. And I'm going to store that as our x vector. And then so for the next iteration, it just takes that and it stores that into the second row of the matrix, and then it's going to fill out the entire matrix that way. Okay, so this is to just run gradient descent. It's literally just a loop with one line of code, really. And if you wanted to keep track of your history, then it's a second line of code to say I want to keep track of this. Okay, but gradient descent, it's really a very, very simple algorithm, but it works, okay? And so if I plot this, I guess, so basically I just create a contour plot, and then we add, I'm adding arrows, and you can see at each of these things we're just kind of moving, and then we see which way is steepest downhill, and we just keep going, and it points down to kind of where the minimum location is. Okay, but as the contours get kind of more and more shallow, you know, our step sizes get smaller and smaller and smaller. Okay. All right. Here we started off with a gamma of 0.1. If we had chosen a different gamma, something that's much larger, we would end up, you know, we run the risk of kind of overshooting or just having a sequence that doesn't perform well. So, so here I've got the exact same thing going on. The only thing I've changed is gamma. Gamma is 0.4. So my gradient is exactly this. But if I do 0.4 times the gradient, okay, rather than subtracting off 1.4 from 5, I'm going to be subtracting off 1.4 times 14 times 0.4, which is going to be 5.6. Okay, so here I'm starting off negative 5, and then I'm going to subtract off a negative 5.6. So that ends up at 0.6, positive 0.6. Okay, similarly, if I start off at 4 and I subtract off you know, 0.4 times 22.5, I end up at -5. And so that actually gets thrown off of the plot here, okay? And so if I, I'm kind of overshooting where I want to end up being, okay? Oops. So let me just. So I end up overshooting there. Let me just kind of illustrate a few other choices. So if I use 0.3, I end up over here. So we're just basically taking the gradient. So I originally had a step size of 0.1, and I took a step size there. But if I change my gamma regarding how big of a step I take, that just takes this line and it just extends it further. So 0.2 will take it twice as far, 0.3 takes it 3 times as far, and so on. On the other hand, you can also just use a very small step size, okay? And you'll just be taking very small steps, okay? And so the issue is that if you take too big of a step, you might actually end up in a location where the gradient at that next location is even steeper, and so it shoots you off even farther away. Okay, and I've got a couple plots illustrating this a little bit later. And on the other hand, if you take a step size that's too small, it will take a ton of iterations, okay? So this was after, you know, kind of like 20 iterations. If you took a smaller step size, then it would kind of follow the same path, except you would have to take twice as many steps, okay? All right, so that's gradient descent just applied to an arbitrary function, and here, now I'm going to apply it to ordinary least squares regression, the loss function, because this is ultimately what we're going for, is we want to minimize the loss function, and we're just starting off with ordinary least squares because that's kind of a model that we're very familiar with, and so we're going to start here, and then then we can kind of apply the same ideas of gradient descent to other kinds of loss functions and whatnot, okay? So here in OLS regression, our loss function looks like this, or if we write it in matrix notation, it looks like this, okay? And so we have kind of the older lectures show exactly how our loss function can be written this way and this way, but here we are, we've got our loss function, and I'll just kind of show you gradient descent what it looks like in both forms, whether it's matrix notation or whether we're using partial derivatives. Okay, so here we'll start with this using the partial derivatives, and so if we wanted to do gradient descent, we would have to find the gradient of the loss function with respect to our weight matrices, W0 weight matrix W, which consists of W0 and W1. Okay, and so this is this is what we're doing because we are trying to find the minimum of the loss function by adjusting the W matrix. Okay, so here our loss function is this. I can just expand out the function itself, which is going to be the linear function W0 plus W1 xn, okay? And then we're going to take the partial derivative of this thing with respect to W0. So if I distribute the negative sign, this is what it looks like. And then taking the partial derivative of this with respect to W0, we're going to just bring the 2 down over here, okay? And this is what we get, okay? The derivative of this ends up with respect to W0 will be this, okay? And so take the 2 down and then apply chain rule, okay, which is just the -1 sign. And so we get the partial derivative with respect to W0 is this thing. And then if we do the same thing with respect to W1, okay, you take the squared value, you bring it down, apply chain rule to W1, and then so you'll have a negative, multiply that by a negative x sub n term, and the partial derivative is with respect to W1 looks like this. Okay, so you have two components. They look very similar, just one has an xn term in there. Okay, so now we have kind of the components for our gradient, where we do the partial of the loss function with respect to W0 and the partial of the loss function with respect to W1. Okay, and that's if you didn't want to use matrix notation. Personally, I think using matrix notation just makes our lives easier, and so with gradient, finding the gradient with matrix notation, we've actually done this already in an older slide. This is our loss function, t minus xw transpose times t minus xw, okay? And then when you expand this out, you get t transpose t minus 2w transpose x transpose t plus w transpose x transpose xw. And then so you take the gradient with respect to w, okay? And so there's no w term here, so that drops out. 2w transpose x transpose t just becomes, or negative 2w, this becomes negative 2 x transpose t. Okay, and if we distribute the 1 over n, and then w transpose x transpose w with respect to w becomes 2 x transpose xw, okay? And then you again distribute the 1 over n. So this is just the gradient applied right here. Okay. And so the gradient descent algorithm looks just like this, where you take your current location and then you subtract off gamma times the gradient, okay? Which, if you're not using matrix notation, looks like this. And we found the components. We found the partial of the loss function with respect to W0, and we found the partial of the loss function with respect to W1. And then so we take this and we subtract off gamma times the gradient, taking a step in the direction opposite of steepest increase, and we'll get our next iteration's location. In matrix notation, you can just say, your current w sub n, and you subtract off gamma times the gradient, and you get the next location there. Okay, so I've coded this up, and I've also have the code over here. I'll probably have to. All right, so just kind of for our example, I'm plotting these 3 dots, okay? 1, 3, 5, 4.8, 11.3, and 17.2, okay? And then just to kind of show you what those 3 locations look like, let me increase my font size here. Okay, so this is what it looks like, and if I did a linear model of t as explained by x, okay, we'll find that the coefficients are 1.8 and 3.1, and if I add a line here, we can see they line up quite closely, but it's not 100% perfect, okay? And so, okay, because the predictions are actually 4.9, 11.1, and 17.3. So we're off just by a tiny bit here, okay? And so for the gradient descent algorithm, though, I say, I write a function that says compute the gradient of the loss function, okay? And this is going to be just a function of the W vector. And back here, we've said the gradient of the loss function. If I just get rid of this constant of -2 over n, it's going to be x transpose t plus x transpose xw, right? So here I have x transpose t. I'm sorry, negative x transpose t plus x transpose xw. Okay, so this is just computing the gradient or something at least proportional to it. Okay, and here I'm going to just start off at some arbitrary location, -1 and 1.5, and I'm going to use a step size of 0.02, and then this is the algorithm. I take our current location and I subtract off gamma times the gradient of the loss function at your current location, and I update our current location accordingly. Okay, I do 1,000 iterations of this, and I ask what is the result of the W vector, and I get basically 1.8 and 3.1. Okay, it hasn't reached there because you know, towards the end we're taking very, very small incremental steps, but here we have minimized this without solving for where the gradient is equal to 0. Okay, so we're just using this optimization algorithm, which just says take it downhill. We had to solve for the gradient. Okay, we did have to use calculus to find this gradient. That's true, but there was no step where we said let's set this equal to 0 and solve for w. Okay, all we're doing is we're just applying this numeric operation of here's our value, so take a step in the direction opposite of the gradient, okay? And that will get us to something that's close to the true answer of 1.8 and 3.1. Is that okay? Plotting this requires a little bit more work, okay? And that's primarily just because of the function of plotting the contour. Or in order to plot the contours, you need a grid of every single kind of value, and so you know you have to create a range of W0 and W1 values. And so here I've written a function to compute the loss vector or the loss function in a non-vectorized way. This is incredibly inefficient, but it just kind of shows how you can iterate through a sequence of data. Okay, so here I've got my observed data as a matrix where I've just did a c-bind of the x vector and the t vector. Okay, and so the loss function is just going to go through every single data point, and is going to be how many data points, how many rows your vector matrix has, and then you start off with the loss being equal to 0, and you just iterate, and you're going to add the squared error. Observed data, column 2 is the actual value, and then over here is the predicted value, W0 plus W1. You know, for your current estimates of W0 and W1, it's going to be your prediction. You take that difference and you square it, and you add that to the current loss. So it's going to just kind of accumulate the loss, and it's going to return the loss value. So we go ahead and we just apply that to get kind of this huge grid of things, and this will create our contour plot, you know, which I've drawn out. Okay, and then if we want to plot the path that gradient descent took, you know, that's a lot simpler because the gradient descent algorithm is again very simple. So here I'm using gamma is 0.01. and I'm saying let's do 500 iterations of this. And now I create a matrix to kind of just record all of our locations. And I start off just at some arbitrary location, -1 and 1.5, okay? Which I think is where I started off over here. And then we're just going to say, all right, for the first iteration, store that into the matrix, wrecord, and then run the gradient descent algorithm. Take your current location, subtract off gamma times the gradient. Okay, so remember we've written a function to calculate the gradient at our current values of the W vector, and then we update our location, our W vector accordingly. Okay. Next iteration we'll store that, and then we update our location, and we just iterate through the entire thing. Okay. And so if I want to plot this, I can just say points. Okay, so points would just create a whole bunch of dots, but here I'm going to say type is equal to L, and so this will connect them with a line, and this is what the gradient descent algorithm looks like. Okay, and so here this is so this here is a plot of the loss function of ordinary least squares regression for this data set of 3 data points. Okay, so we have three data points, and we can calculate the total squared loss. And if I used a different set of parameters, okay, so if I used -1 and 1.5, and I don't even know if I can do, if this will even appear on our data set. Okay, if I have -1 and 1.5, and we'll say color is equal to blue. Yeah, this doesn't even. So this would be kind of the fit line over here. Let me just. Okay, so here are okay, so these are our 3 data points, and if I plot this is kind of our initial fit line. Okay, and so we could see this is going to have the squared loss is going to be quite big, and so as we follow the algorithm, okay, this is the path that we take, okay, and you can see that kind of the path that we're following indeed forms perpendicular lines to the contours, okay, because we're following the path, and so out here these the contour lines are almost parallel to each other, okay, and so we're following this path that's perpendicular to the contour lines, and then when we get here. So out here, this is we're basically changing the intercept, okay, and over here we're changing the slope. So we started off with a slope of 1.5, and so when we're out here, it's basically saying that in order to get improvements, it's more important to change the slope. Okay, so at the next iteration, we might go here. And our slope changes from 1.5 to 3, okay? Whereas our intercept, only shifts a little bit from around -1 to around, I don't know, 0.5, 0.7-ish or something like that, okay? So if I change this to, say -0.7, and change my slope to 3, okay? At the maybe I'll do purple, okay? At the next iteration, we're getting to something around here, okay? And we can see this is a dramatic improvement in terms of the loss that we've observed, okay? So it pushes up here and it says we need to kind of dramatically increase our slope. And so once we get to a slope of around I don't know, 3.5-ish or so, okay? Then it says, you know what, now we don't need to focus on adjusting the slope as much anymore. Let's kind of adjust the intercept. And as we adjust the intercept, we do need to kind of decrease our slope. So when we get to here, our slope is probably around, I'm just eyeballing this, 3.7, and our intercept is maybe around 0.2, okay? So negative 0.2 and maybe 3.7, and I don't know what a good color would be. We'll go ahead and do orange, okay? And so we're kind of around here, and now we're saying, okay, let's adjust and decrease the let's decrease the slope a little bit, but let's also increase our intercept. So maybe at the next location we're going to kind of just test out, we're going to say, let's use a slope intercept of 1 and a slope of maybe 3.4-ish, okay? So if I increase the intercept, I push the intercept up to 1, I probably want to decrease my slope, and maybe I'll use red here, okay? And so we can start to see that, you know, now that we're up here, we're going to just kind of angle our line a little bit more and more and more until, you know, we're decreasing our squared error, okay? Until we get to something around the optimal solution, which is going to be at the location 1.8 and 3.1 for the slope, okay? And so that's what gradient descent looks like. You know, we just started off at this terrible location, and we're just saying, okay, what we need to do is we need to kind of crank up the slope, and then we'll adjust our intercept and kind of shift this around accordingly. Okay, that's using a gamma of 0.1. I want to just show you what happens if you use a gamma that's a little bit too big. Okay. And so here, on the next slide, I'm going to start at the same location of -1 and 1.5, okay? But I'm using a gamma of 0.05, okay? And so what happens here is that, you know, I take a step that's perpendicular to my, you know, kind of the current contour line, but I kind of take a step that's too big, all right? And I end up out here, okay? And so if you imagine kind of the bowl that represents the loss function, you know, I'm starting on one end, and I take a step that rather than going, taking a step downhill, my step is so big, it's like I'm this giant robot or something, and I entirely skip the kind of the valley of the bowl, and I end up on the other side of the hill, okay? Or the other side of the valley, and I end up on the hill. And so now I have to say, okay, well, which direction is downhill? And now it's pointing in the opposite direction, okay? And so I take a step in the opposite direction, and I end up over here, okay? Luckily, when you know, when I take a step downhill, I end up on the other side of the hill, but the other side of the valley is less steep, and so it does kind of dampen out. And I do eventually start heading towards the optimal solution here, okay? On the other hand, if you set your gamma to be even larger, you get the opposite problem where it's even more extreme. So you start on this side of the valley, and you want to say which way is downhill, and it says you got to go this direction. But then you take a step that's so big that you end up on the other side of the valley, and when you end up on the other side of the valley, you're at a place where the slope is even steeper. And so when you when you end up over there, the gradient's going to say, okay, well, you need to take the gradient's going to be even larger, and your next step that you take is going to be even bigger. And so you get this opposite problem. So for that one, I start kind of over here where the slope is small, but you can see I take kind of a step in the wrong direction, and I end up too far, and then and with each step it gets just larger and larger and larger, and you can see things just kind of end up badly. In this illustration, the steps that we take are too big with respect to one direction, but not in the others. So we do get better values as we talk about kind of, if we look at the relationship between the slope and the intercept, we're getting, they seem to converge over here, but we can see they're diverging in the opposite direction as well. All right. Is that okay? All of this stuff about the gamma. And so one of the tricky things with using gradient descent is figuring out your learning rate. Okay. This gamma value, we call this the learning rate or the step size. And this is what we consider a hyperparameter. This is something that we have to specify regarding how our algorithm will work. And so, we'll have to talk about how that works. But basically, in the beginning, it's just kind of trial and error. Okay, you just kind of that's kind of how we select our hyperparameters. Should I use gamma 0.01 or 0.05 or 0.07? It's trial and error. You test one out and you see how well it performs. So maybe you started off too small. You say, okay, I'm going to use something bigger. Then you use something bigger and it's too big. So then you kind of adjust back and forth. Okay, so far what we've done is we've used calculus to figure out the gradient. We either used calculus to find the partial derivatives, or we used calculus to find the derivative with respect to the vector. Okay, and that's going to be the recommended method for doing gradient descent. Is you're going to have to figure out the gradient using calculus. However, sometimes you go through the calculus and you're not sure if your answer is correct, okay? Especially as the problems get more complicated, you might begin to lose confidence in your calculation of the gradient analytically. And so one thing we often do is we'll do numeric gradient estimation. Okay, and this is just a mechanical way for estimating the gradient at a certain location. It's an inefficient method, and it's not recommended at all for trying to use it in kind of the actual algorithm. But it is a very useful tool to kind of just make sure that the gradient you calculated via calculus makes sense in the first place. Okay. And so if you just kind of recall how a derivative works, is the derivative is this limit as h goes to 0, and you can approximate the derivative just by taking some small value of h, say 10 to the negative 5. You throw that in there and you'll get an approximation of the derivative. Okay, the gradient works in the same way, okay, except now you have multiple components. So here I've got the function f, which we'll just say is a function of x1 and x2. And basically, the gradient consists of the partial of f with respect to x1 and the partial of f with respect to x2. So for the partial of f with respect to x1, you do what's f of x1 plus h, leave x2 alone. You subtract off f of x1, x2, and you divide by h. And then for the partial of f with respect to x2, you have f of x1 and x2 plus h minus f of x1, x2 divided by h. Okay, so you're basically just going to find the derivative or the approximate derivative or partial derivative for each of these values. Okay, and the important thing here is that you do one component at a time. You do not do x1 plus h and x2 plus h. You do you'll kind of adjust, or we might say perturb x1 by h, okay, and you leave x2 alone, and then over on this side you perturb, or you just add a tiny h to x2 and you leave x1 alone. Okay, so it's very important that you do these one at a time. Okay, so just to kind of illustrate, we'll go ahead and go back to the function that we saw at the very beginning of the class, which was here. and we said, the gradient of this arbitrary function at -5 and 4 is -14 and 22.5, okay? So if I just plug in -5 and 4, we're going to get 85, and basically I perturb the -5 by 0.01, so I'm going to run f of -4.99, okay, and comma 4, and I compare that to f of -5, comma 4, okay? And so here I get 84.8601 minus 85, and that's going to give me an approximate gradient of -13.99. I do the same thing over here, and I leave -5 alone, but I perturb 4 by 0.01. Okay, so I'm going to have -5, comma 4.01, and that gives me 85.225 minus 85, and I divide by 0.01, and so I get -13.99 and 22.525, which is approximately equal to what we calculated analytically, which said our values are -14 and 22.5. Okay, so if I were to see results like this, I could be confident that my analytic approach to the gradient is correct because it matches kind of this numeric gradient check. Okay, we'll go ahead and end there for today, and we'll see you guys on Friday.